in today, this kind of like it is the finish up of the previous class, but the next one is going to be a new content for everyone, associative forecasting. So this one, and we will use this model when the changes in one or more dependent variables can be used to predict the changes in the dependent variable. So we said one or more independent variables. Actually, in today's in-class practice, I'm going to only look at one independent variable, one dependent variable. So, and there is one more regression analysis. You can include more than one independent variables. I don't have much time of doing that, but will be very similar. So we will focus on just one kind of like one independent variable, one variable. So, and this is the technique we are going to use over here. It is a linear regression analysis, but we only pick one kind of like dependent variable. So we apply this technique just as we did in the time series example. When you choose the independent variable, they are kind of like associated with time as well. And for this model, we are going to establish in today's class, we call it least square techniques. And then use this technique, we are going to get a regression model. This regression model, however, is a very simple model. We only include one independent variable. And this y hat, it is our prediction, our interest. We want to see and want to like make the forecast of this one. We call this is a dependent variable. So, and x, it is independent variable. And we all understand from algebra. This is the linear equation. A, it is the intercept. B, it is the slope. And here, if you see, and this is kind of like drawing of y. This is y equals to and a plus and bx. And here it is a value. So intercept. And b, it is the slope of the change. And we call this the least square method. When you look at this this chart, you see all the stars. These are the stars representing individual observations. This is at year 1. You have the actually data. It is corresponding to this one. Okay, at year 2, it is corresponding to this one. So every single star, it is the real observation. When we look at these stars, they kind of give us a kind of like a trend. Okay. Let's try to make this trend as a linear, like a line. And why we call least square is because we try to make all of the deviations. Okay, this is the error. When the real number is over here, but the prediction give you a data is over here. So this is the error or deviation. For the next point, okay, at year 2. The real data is at this location, but the prediction will give you the point corresponding over here. So this is another deviation. For every deviation we call them error, correct? And we can calculate the error 1 and error 1 square and error 2 square, error 3 square, and error 7 square. All of the 7 deviations, we take the square and plus all of them together. And we can use the mathematical approach to make sure this and this mean, this like a square errors are minimum. Okay, so the equation should be E1 square, E2 square, plus E3 square, plus E7 square, and we can make this entire like a sum to be minimum. This is the least square method. When you make this as a kind of like a minimum square values, you can get the A value and the B value. Remember what is A, what is B? A, it is the intersection. B, it is the slope. That's how you decide A and B. And the least square method minimizes the sum of squared errors. That's what I mean over here. So the green kind of like a statement on the screen, if I'm using the mathematical kind of like equation, it's just like this. And well, we don't have to go so in detail how you use mathematical equation, but we can obviously use the mathematical analysis result. The result we can get, it is the linear equation y hat equals to a plus bx, and b, it is this number, and a, it is obtained by using y hat, y average, and subtract b times x average. So when you look at this sigma, and most of the students, they don't like to see it because, so, oh, what's that? Well, sigma just means sum, means add something together. So how about this one? Sigma square is also something you add something together. And I'm going to use an example to show you, Excel can easily help you to finish the tasks of calculations in B and A. So, and I look at the slides over here. So how do you calculate the example? This example is to say the demand for electrical power at New York Edison over the past 7 years is shown in the table. So electrical power demand. And the firm wants to forecast the next year's demand by fitting a straight line trend to this data. So our goal is using the year from 1, 2, 3, 4, 5, 6, 7 to predict what will happen in year 8. So, and we can put all the columns in Excel. So you don't have to do it right now. I have already prepared the raw data for you. So when you see over here, because we need to calculate a sigma y and the sigma x from the equation, and in the equation, and b equals to and sigma xy, and subtract n average x, n average y divided by sigma x squared, subtract n and x squared. So this is the equation. So you see, in this equation, we need to calculate a sigma xy. How can we do it? Wait. So we can generate a column xy, which is x times y. And then, and in this equation, we need to calculate x bar and y bar, which means average. And in this equation, we need to calculate x squared. This is x squared, so this is x squared. And then you need to sum, and then just add them all together. So Excel can help us easily to complete all of the calculations. And after we do the calculation, we can find out A and B. After you get A and B, that means you determine the linear equation, right? So let's do all of the in class 7. Can you open? So suppose these two should be blank, and you are only given x and y, right? So from the example you see, if you look at your handout, you are given only 2 columns. But you need to prepare an x square and x bar and x average and a y average and sum. So let's do this, x and a square. So x squared means your x times x, right? And y, x times y, this column, just simply and put these two together over here. And in your equation, you find out, and we should first calculate b, and then calculate a. And in b, this is the big equation. In b equation, you see sigma xy. That means all of the x times y together, and then you add them together. So this is this one. It is the sum of and x and y. In this equation b, another one, it is n times x bar and y bar. And bar means average. So we can use, you can use sum of this, x, and divided by 7 data, n equals to 7. So average. And y, we also need to choose to find out y bar. So y bar equals to sum divided by n. All right. And when you look at x squared, so x squared, and you see in the formula of b, denominator is sum x squared. So, and then you need to find out what is the sum of x squared. So it is this one. So now we pretty much find all of the information we wanted to calculate a and b. So we need, in this formula for b, we need sigma xy, so which is this number. We need n times x bar times y bar. So these two. And in the denominator, we see it is sigma x bar. Here's minus and x bar square. So let's do and put all of the equations over here. For b, you want to use is sigma xy and minus n equals to 7 times x bar and y bar. This is your numerator. Divided by denominator, it is sigma square x square. And subtract 7 times this one and square. So this is your b. The answer for b, it is this one, the coefficient in this model. And also you say it is the slope of the prediction line, right? B.
Can we go back to the equation?
Here. So I can make the equation a little bit bigger. So after we finish the slope calculation, we are going to use the formula to calculate what is the intercept. When you look at the formula, A equals to y bar average, subtract B you just calculated, and subtract x average, and go to Excel. So equals to y bar. So this is y bar, subtract, and B times, and this is this B7, here is and y bar, subtract B times x bar. So the result B equals to 10.54, and A, it is the interception 56.71. Which one, average? This average equals to 28 divided by 4. Okay. And the next one, 98.86 divided by 7. So because N, it is how many observations? The number of observations in this example is 7. Are we okay? Can I switch back to the PowerPoint slides? So using this equation, we can plug in the number of year 8, because we are going to use the 7 years historical data to predict what will be the electrical power demand in year 8. Then you see from this equation is 8 over here. You plug in this number. Now you say, oh, in year 8 the demand will be 141 and megawatts. So this is an example of least square example. We use the existing kind of like a historical data, try to find out this linear line. Linear line, we call this is the trend line. And then this trend line can give us the idea, okay, what will happen in next year. So that's the application. For the least square requirements, and we always try to generate a linear regression. Linear regression means y equals to a plus b times x, this linear line. So this is the linear relationship. That means you only have y equals to a plus b times x. There's only one independent variable. And if you have the you have multiple variables, you will not generate a linear line. So we do not predict time periods far beyond the database. So you cannot use the existing 7 years data to predict how about 10 years later. No. And you only predict something in the near future, in year 8 or year 9. And but you don't want to predict in 10 years later. So it should be, close to the database, predict the time, in the near future. And the deviations around the least squared linear lines are assumed to be random. So if you learn statistics in the higher level of the class, probably 4,000 level or 5,000 level on campus, you understand why we wanted to have a random. Random means, okay, and whatever the errors or deviations is caused by uncontrolled random error. If you see some special patterns in the residuals, that means, okay, your linear regression line is not good enough. You need to include some other terms in the regression model. So that's all. That's kind of like more statistics background involved in that one. Just give the three kind of like summarizations about least square methods. And the next example, so which is the second practice in class number 7, we are going to talk about seasonal variations. So seasonal variations can adjust the trend data for seasonal kind of like variations in demand. For example, some of the goods, they vary according to season, and like the winter clothing, some kind of like fashions, you have to consider different season. And turkey is very popular in around the spring, like Thanksgiving break, that time. And it's not yearly around very popular in grocery store. So these are the seasonal informations. And so when we use, when we consider seasonal sensibilities, typically we use the 4 or 5 steps over here. First, we want to find out the average historical data demand for each season. I should not just, this is from the book, each month, okay? And maybe the season, and then they call it is by month. Could be the season is spring and the summer and the fall and the winter. And also can be Monday, Wednesday, Monday, Tuesday, Wednesday. So season means, okay, something around your period of time. So we can say, find the average historical demand for each month, or you call each season, depending the data you are processing. And then we compute the average demand for all of the months. And the third one is try to find out the seasonal index. This is the key part of the calculation. How you use the seasonal index to adjust the average demand. And then we are going to get the estimate for the total demand next year. And then use the seasonal index to derive this demand for the number of months, and then times the seasonal index. So this is the example, and I think we have the example is from this is said. A distributor of Sony laptop computers want to develop monthly indexes for sales. Is distribution center for computer sales. And the data from 2007, 2008, and 2009 already available. And assume the demand for 2010 will be 1,200 laptop computers. We want to find out each month to predict the demand for each month in 2010. Okay, in this existing data, and here we can calculate the average demand in the past 3 years. So 90, it is the average of the past 3 years. And then you can find out every month, okay? And then we can find out what is the total average annual demand. Then total annual demand is everything added together from January to the last month, December. And then what is the average demand? So if you use the total 1128 divided by 12, so this is the average. Average monthly demand in the past, historically. So you can find out. And then the seasonal index, it is the average seasonal or monthly kind of like demand divided by the overall demand, average demand. So this is what we call index. For January, the index should be, okay, here, the historical data of January in the past 3 years divided by the overall monthly demand. And for February, you use 80 and divided by the average. So, and then we fill out all of the seasonal kind of like index. So after this, and then we have the forecasting for 2010. It is 1,200. So 1,200 by average, and each month will be 100 computers over there. But this 100 just give you the rough average, and every month the average. You need to consider seasonal variations. The seasonal index will give you the seasonal kind of like a variation. Use 100 to times this index, that's 96, and then divided by 12. And now they see, oh, April is a bigger number, and April will have a kind of like a higher demand. So May is 131 demand. So, and now we see even the next year average of the per month computer, it is 100 computers per month. But some of the months they need more, some of the months they need less. Okay, so we are going to practice this one. And go to the second tab, seasonal variations. We are going to practice this. And according to the 5 steps, the first step is to find out the average historical demand for each month. If it's season, spring, summer, and fall and winter, could be the average of each season. So you can use the average function directly without using the sum function. Are we okay? This average function? And then I will just quickly, you can use 2 approaches to fill in the rest of the column. You can drag and move your cursor around from the big cursor to be the small cursor. Now you can double click. Okay. So this is the average demand for each month. And now I'm going to have the sum function for of the total. That's the sum of the average period demand. Now we want to find out how about we spread it out the 1, 1, 12, 28 to be every month equally. So use this to divide by 12. Oh, see, I got some error. I just want to demonstrate this error to you. I cannot drag my formula directly at this moment, because when you drag and Excel is going to shift your formula and one space and in the row. So it is E16 divided by 12. And if you click the next one, it's going to be E17 divided by 12. E17 is 0. That's why you got a 0 over here. So what happened over here is what we call E16. This like an index is a relative index in Excel. But I want to make sure I use E16 every time. Then I really want to use it is absolute index. I don't want to E16 change. And make sure your cursor is blinking around E16 and hit on your keyboard F4. What do you see? Yeah, there are $2 are added in front of E and in front of 16. Now originally was E16. It is a relative index. Now it becomes what we call absolute index. So if you shift your Excel and formula, if you double click at this, you will see. And every single kind of like cell they use E16, E6, E16. It will not change. Okay? Can we move to the next column? The next column we want to calculate is the seasonal index. So which is, and whatever the month divided by the average monthly demand. So and it's E4 divided by F4. Did we get this done? This column? Are we all right? Yeah, okay. Then the next one, it is the final demand. The final or your real prediction after considering the seasonal variation should be, and because 1200, it is the given number, correct? In this setup, they said in 2010, they predict the overall yearly demand, it is 1,200 computers. So each of the month, it is 1,200 divided by 12. You use this number to times the index. So index times okay. Can you hit the enter key? Now you want to make sure it is the integer number, because computers, I think they are, single computer, no half computer doesn't make sense if you give a decimal point. Normally round up number integers and will give the idea over here. So this is the subtraction. This is the homework you are going to finish, not homework. In class 7, I want you to submit at e-learning in 7, okay? Do not go to the wrong folder. So I see so many students, I submit my work into a different folder. Okay, so, and this is the submission in class 7. The seasonal index and the purple one, it is the forecast of using year 1, 2, 3 to forecast in year 4. It is, that's the kind of like a plot if you use the line chart. And for forecasting in the service sector, and there are more kind of like considerations. So more factors. For example, and some of the industries, they need to consider what is the holidays. And holidays in, like for Mother's Day and Father's Day, these are all right because they are all Sundays, okay? Restaurant and the flower shops, they can prepare for on Sunday. So some other holidays, maybe it's not on like a Sunday. And then, and it could be like a varied time, okay? And Valentine's Day, some other celebrations you will see. So it will impact the restaurant or gift shops like peak time or peak hours or demand. So, and there are special considerations that we need to take into account for service sectors. And it's for fast food industry, they want to use a very short kind of like period of time to predict the demand. And for the lunch hours is high peak. And also the evening hours is high peak. And then we need to consider this as the staff like arrangement, or okay, and Saturdays and Sundays. These you need to consider how to prepare the supplies, have enough supplies, and but do not overstock your supplies because the groceries you don't want to hold a very long time. Okay, and these are the forecast. So, any questions for today's in-class work? Practice? Submit at in-class 7 at e-learning. But I'm not done within today's class. I want to let you know, okay, Thursday, this is Thursday, I have to go to a training. I have, tomorrow the training will be 3 days training, and Wednesday, Thursday, and Friday. I will give a video demonstration at e-learning, capture the video about in-class practice 8. So you will follow my video. You can come to this room or go to your own home computers and follow that demonstration, finish your work, submit at e-learning. That's the work you need to be done, okay? You need to do that part in class 8 on your own, follow the video, Panopto video at e-learning. And the rest of the time, I want to go ahead and look at our homework in homework number 4. So this is the homework number 4. And I look at over here, it is just plot the monthly sales data by using Excel. You can put it column 1 and column 2, highlight the column, and then you click insert, and then it will give you certain options, what to plot. You need to use your own judgment. I think it's very obviously you can use, the line data to plot the data. And then B, it is forecast the January sales using each of the following kind of like approaches. One is using 3 months moving average. This is one of the in-class practice we did already, correct? Moving average. And this is the second question. And I wanted to use a 6-month weighted average using 1.1, 0.1, 0.1, 0.2, 0.2, and 0.3. So, and using the given average to forecast the most of the months. So this is the weighted average, correct? How many points you need to use? 1, 2, 3, and 4, 5, 6. So you use the 6 and to predict the next one. And then using the 0.3 as the recent heavy kind of in a high weightage value to apply that to the recent data. So 0.2, 0.2 will be closer related recent data. 0.1, 0.1 will be January, February, and March. So they are far away from your prediction. So this is weighted average.
Oh my gosh, I
Yeah.
Okay, so for each of the 6 months, like the 6 months, I had this 6 times 6, and then times 5 times 4.
No, times 0.3, times 0.2, times 0.2. Yeah. Mm-hmm.
Oh, okay.
Yeah. And number 3 is to try to use the exponential smoothing like a model, remember? And it is a prediction value equals to, and using the alpha equals to 0.3, which is, prediction and plus 0.3 times and the real number and subtract the prediction number, and but the and the forecast and the September forecast of 18. So use this one to, it is the exponential smoothing. And the last one is trend projection. What is a trend projection? We just learned today, correct? And then you are going to generate a line y equals to a plus times b, times x. So, and you need to plot this data and then solve each of the problem and one by one, and then come up with the model. Okay. This one. Second problem. George K owns a company that manufactures sailboats. Actual demand for George's sailboats during each of the past 4 seasons. The data are given over here. George has forecasted the actual demand for his sailboats in year 5 will equal 5,600 sailboats. Based on the data and the seasonal model, what will the trend level be for in year 5? This one is similar to today's practice, right? Today's practice, we calculated the seasonal variations is by month, January and February and March and so on and so forth. Here, we do not really care monthly variation. We care about spring variation, summer variation, and and the fall and the winter. So it's exactly same seasonal variation, but in terms of 3 months, it's not just 1 month. I think that's all I want to explain to you and about our homework practice, and which will be due on this Thursday, right? Make sure you submit your homework and by the due time. And during the training, I probably have little time access to my computer or email. I may not may not be able to respond to your email very quickly. So, and I hope you still can finish your homework number 4 by the due time. And so this is today's